Howdy, y'all, and welcome back to another lecture on Intro to Observational Techniques, ASTR 124. I am Dr. Rob Parks. Today we're going to be talking about charts and catalogs. And more specifically, I'm just kind of going to run through a couple of resources that astronomers use in order to gain information and more specifically plan observations of various objects. So since the early days of Hipparchus, astronomers have been cataloging the sky in any number of ways. At this point, there are quite literally hundreds of thousands, tens of thousands, maybe hundreds of thousands of catalogs, and I can show that to you later on. But these catalogs are developed for various different reasons. The first catalogs were developed specifically for positional information. Where are these stars in relation to other stars, particularly within, say, constellations and the like? So one of the first catalogs that was put forward is the Bayer catalog. And if you want more information about these from kind of a historical standpoint, I recommend reading the relevant chapter in Observational Astronomy by Bernie Gonzalez and Osper, second edition. You may heard of stars like, you may encounter stars that are named things like Alpha Orionis, Beta Pic, or Beta Pictoris, these sorts of things. The designation is that the catalog was produced not telescopically or really quantitatively, but it basically, there was a gentleman who looked at the night sky, looked within a certain constellation boundary and said, that star is the brightest star that I can see. Therefore, that is Alpha. Next star is Beta, so forth and so on. In the constellation of Orion, Rigel is designated as Alpha Orionis. Betelgeuse is designated as Beta Orionis, and so forth and so on. There are small occasions where if you actually look at the values, the numerical values of brightness, it's not quite in the correct order, but it's at least a first blush, a first try. So if you hear something referred to by a Greek letter, you know immediately that star is real bright. The next one is the Flamsteed designation, where they are numbers. So if you're into exoplanets like I am, the most famous one at this point, well, TRAPPIST-1 is arguably more famous, but the first exoplanet discovered around a sun-like star was 51 Pegasi b. The 51 indicates a Flamsteed designation. That means that going from east to west, it is the 51st star in right ascension. So the numbering system is effectively the order of the star as it rises. So the first star to rise in the constellation is 1, the second one is 2, and so forth and so on. So it's the 51st star to rise in the constellation of Pegasus. Then you get the Henry Draper catalog and so forth and so on. Like I said, I don't want to really bog down this lecture with that. If you are interested in those, then definitely go to the text. I will say that HD, which is a very common designation, is the Henry Draper catalog. Other common designations are HR and SAO, things of that nature. But let's get into some tools that astronomers actually use. Let's go with that one. So the primary tool, such that I actually have this bookmarked on my upper bookmark bar, is SIMBAD. And you can also do SIMBAD astronomy. The first hit should get you there. SIMBAD Astronomical Database. SIMBAD is more than likely a backronym, but it's French, so I have no idea what it would actually stand for. I've never really looked into it. But it's basically a database of all stars. Given that the target of Gaia, a satellite that is interested in parallax, has billions of stars, This has literally, quite literally, has a database of at least hundreds of millions of stars, if not a billion. So pretty much every star that we know of or have looked at. You can query this database by any number of ways. You can do it by identifier, basically name. You can do it by coordinates, therefore, so forth and so on. I'm going to do basic search. And so this is basically the name. Now I will go to I will illustrate what I refer to as my second wife, which is Lambda Andromeda. So this is the Bayer designation. We frequently truncate those names. So Lambda Andromeda becomes Lam and. So effectively we truncate them to 3 letters each. The Greek word goes to 3 letters. The constellation name goes to 3 letters, generally speaking. I click enter, and I get this. So the bold is the name. You notice for this star there is an asterisk in front of it. What that designates is that this is a variable star, meaning that it changes its brightness over time. The phrase RSCVN variable is a rough designation of what type of star is it. Variable stars have, or in many cases, variable stars have a prototype, basically the first type of variable that was discovered in that class. And generally speaking, that class is then named after that. So for example, Cepheids are pulsating variables. Cepheids get their name from the first one that was discovered, Delta Cephei. This particular type of variable object, which is an eclipsing binary with star spots, is known as it is a binary star with star spots, not eclipsing necessarily. It is, the first one discovered was RSCVN, or Canis V. You can Google it. I can never remember exactly what that constellation is called. But it's Canis something or other that starts with a V. Again, it's truncated to CVN. Now, one designation that I failed to get into before was this RS business. And RS is a way of designating variable stars. So in that particular constellation, the first variable that was discovered would be A, CVN, then B, then so forth. And since variable stars are plentiful, effectively there are more than 26, more than Z. And so once the star after Z has been designated, the next star is AA, then AB, and then so forth and so on. And this is RS. So if you're interested in it, you can do the math and you can figure out where this variable lies in its number of discovery. But anyway, that is a rough designation. I say rough because I am not entirely certain how this database gets updated, but from my own personal experience, I have noticed a number of times where that designation is incorrect or not specifically correct. My point is, take it with a grain of salt. Don't look at that and say, oh, it is absolutely an RSCVN. With all of this, you need to, if you want to do real science with it, you need to look into all of these values and verify them. As Mr. Reagan used to say, trust but verify. Down here, you have the ICRS coordinates. Those are the right ascension and declination with errors for epoch 2000. Now, what that means is that because of precession, the coordinates of stars are constantly changing based on the motion of the Earth's axis every 26,000 years. An example of this is the precession of the equinoxes. Because of that, astronomers pre-computer days basically created a catalog of right ascension and declination and then published corrections, an equation that would correct, or rather give you the updated value given that from that catalog. So for example, the next one down is FK4, which is an epoch of 1950. So let's say it's 1976 and you want to know where this star is. You would take the coordinates listed as such, and then you would compute what the changes of those of the position of the star based on precessional motion. So there's an equation, you'd stick in the numbers, and bing, bang, boom, you'd have the values, the updated value. But in this day and age, this is done automatically through computers. And so frequently with TCS systems like telescope control systems like the Sky and others, you will have a current value. It will give you what is the position of the star object as it is right now, including precessional motion. Stellarium also, I think, has this as well. But given the size of the motion within a grad student's lifespan, it'll get you in the right area, particularly also given the pointing errors on a telescope. You also have galactic coordinates. You have the proper motion of the star. Anything in brackets is the error associated to that value. So this is the motion in milli-arc seconds per year of the star in right ascension. This is the motion of the star in declination, again, in milli-arc seconds per year. You may have noticed this blue thing over here. This blue thing is a reference. In this case, that reference points to the Gaia early data release 3. This is the satellite that I was talking about before. So the values that SIMBAD is displaying are the values that were found using the Gaia telescope. It is essential, again, if you are going to actually do science here, it is essential that you look into these references to make sure that they are up to date, accurate, and so forth. You have the radial velocity, essentially how fast it's moving away or towards us. In this case, it's moving away with a value of 6.84 kilometers per second. You have the parallax in milli-arc seconds. Again, this is the error. This is a estimate of the distance to the star. You have the spectral type. The spectral type tells you, roughly speaking, how hot the surface of the star is and where it is in its evolution. So a G8 Roman numeral 4 star is a star that has a surface temperature about 1,000 degrees-ish Kelvin less than the sun. And the Roman numeral 4 tells you that this is a slightly evolved star, meaning that it is no longer burning hydrogen to helium in its core, but is rather has an inert helium core with a hydrogen burning envelope, and it is moving up what we refer to as the red giant branch. Spectral typing gets real complicated. That K, I honestly have to tell you that I don't know what that K stands for. I can tell you that P stands for peculiar, meaning that the metallicity of the star is a bit wonky in comparison to others of its type. So yeah, far beyond the scope of this. But anyway, it gives you the spectral typing. And then it gives you the magnitudes, the brightnesses of the star. And some of them will have errors, some of them won't. Again, you want to click on the link to make sure that you know where this is coming from. When I get into the magnitude system in the next lecture, I will start talking specifically about some of the things one needs to be aware of when taking magnitudes from SIMBAD. Down here, if you were to scroll down, you get all of its lovely identifiers. Basically, what is the name of this star in various catalogs? And you can see this is but a few of them. You can see, but it is illustrative to note that there are a lot of catalogs. You have Lambda Andromeda. It's also 16 Andromeda. I lovingly knew it as HD 222107 in papers and telescope proposals and so forth and so on. This also gives you an indication of how well studied this star is. If it's a lot of identifiers, you know this star is very well studied. If the identifiers are maybe a dozen or less, this star is faint and probably hasn't been looked at a lot. References. This is the biggest caveat to SIMBAD. Generally speaking, I trust pretty much what SIMBAD is telling me. But sadly, I don't know how they do this, but one of the most important, internet's slow. One of the more important things that SIMBAD can give you is called references. And references is, as you can see, a fairly up-to-date list of papers that deals with this star. So theoretically, all of these papers should either has something to do with Lambda Andromeda specifically, or Lambda Andromeda was one of the target stars in that study. What I have found is that's really not always the case. There are a significant number of examples of papers that actually have nothing to do with Lambda Andromeda. So I, generally speaking, don't look for references of Lambda Andromeda within SIMBAD. I actually do it using NASA ads, which I will go over later in the course in a future lecture. But it is a fairly good starting point, particularly if you could find one that actually has Lambda Andromeda in the title. Which I'm not really. Here we go. Oh, look. It's from yours truly. Interferometric imaging of Lambda Andromeda, evidence of star spots in rotation. Great read. Highly recommend. Anyway, so if you want a starting point, you can click on that link. It goes to the paper, and you can read it. But if it's not exactly what you're looking for, if you're trying to study Lambda Andromeda for reasons other than star spots, I don't know why, but if you were, then there would be links within the paper that can be used to look into various other aspects. And so forth. I am going to back this up because that is a huge space. The next thing comes down to that's relevant is collection of measurements. So I'm just going to click on display all. And this gives you, if you scroll through all of the references, generally speaking, this doesn't always display. Here we go. You get values, like for example, the radial velocities, you get the size of it, of the star, you get the distance to it, rotation rate, metallicity, so forth and so on. And you can see that these values are not absolute. These values are different based on the study that was done, and those studies have references. The thing to note is that there is, generally speaking, a consistency, that these values are roughly around the same number, and they are consistent within errors. But it is illustrative to show that, one, how well is, say, the metallicity of the star known? Here it's known pretty good, but it could, there's been some spread in the value. But again, go to the reference. That'll tell you how the metallicity was determined and the error of that metallicity, and you can go from there, so forth and so on. You can see spectral typing. Generally speaking, it's agreed that the star is a G8 giant subgiant, but there are some studies that have, including recent ones, that have stated as else. This is not a absolute reference. Like, this is not all of the studies that were done on this. Again, it is but a sampling. I'm not entirely certain how the database updates itself or what studies it decides to display and what else. But again, SIMBAD is a great, think of it as sort of the Wikipedia of astronomy. It is a great starting point. It allows you to quickly find estimates of various characteristics of the star, and that can then inform you as to where to go from there. Do not take SIMBAD values and use them absolutely, meaning that if you were to write a paper, do not quote the values in SIMBAD and then cite SIMBAD as your source. You always want to cite a particular study that was used to determine those values. Now, what about finding a star? There, you want to use something called ALADIN. And this is a preview of it on the right side. If you go over here, you see these two arrows. You just double click on that. And that brings up a star chart. These star charts are generally speaking, from the Sloan Digital Sky Survey, which was a photographic all sky survey that has been updated once. And so that gives you an image of the star and its environment. Couple of things to note with this, a couple of tools to note with this, if you're going to use this as a way to plan observations. First one is, I'm not going to move the cursor. Why not? Move the cursor. There. You see that this is the right ascension and declination. When I hover over it, that tells you what the right ascension and declination of the target star is. In this case, Lambda Andromeda. If I were to move it off, that tells me what the right ascension declination is underneath the mouse or the cursor. Over here, you may not see that very well, but that says SIMBAD. If you click on it, let's see, there we go. You'll notice these green boxes that appear. And what that does is it tells you that these stars have SIMBAD designations. They are in the SIMBAD catalog. So the number of stars in the catalog may actually be substantially smaller than I mentioned before, but it's got a lot. But it does not have all. So, for example, this star doesn't have a green box, so it's not within SIMBAD, but this one does. So if you click on it, you get to this designation, which stands for the Tycho catalog, and that's its designation. Effectively, that's a truncated coordinate system. I think it's galactic, but again, you can look into it yourself. If you click on this link, this goes to the SIMBAD page for it. So, for example, here we have the SIMBAD information relative to Tycho. You have its position, you have its magnitudes and the errors and so forth. And I will get into why that's important in a moment with respect to the class. The other thing to note down here is the very little corner. Again, you probably can't see it in the video, but it says FOV, which stands for field of view. Field of view is what we call the size of the sky or area of the sky that you are currently viewing. So obviously we're looking at a small portion of the sky. More specifically, we are looking at a portion of the sky, and I believe this is length. You can see that it's the aspect ratio is something like 16:9. The 16 corresponds to 16.9 for arc minutes. So if you go from left to right, the size on the sky, the angular size on the sky is 16.94 arc minutes. You can scroll. And so this is my internet being slow as to filling in the gaps. Eventually it will get there. The digital sky survey was taken in slices or chunks. And so apparently my internet is not cooperating, and it's not giving me the rest of the sky, or at least it's not loading it appropriately. But you can see down here that the field of view now is 2 degrees. And so you can adjust this to zoom in or zoom out. Most relevant is this is a star chart. Now, prior to the interwebs, astronomers would use paper star charts. Oh, I was going to get one, but I don't know how well it would display here. Paper star chart is a white sheet of paper that has the map of the stars on it in black over white, because that is a better contrast, so you're able to see the stars more distinctly. And they are used to be able to identify what your not only what your object is, but comparison objects in that field. For Lambda Andromeda, it's pretty easy to find out which one it is. It is the bright one. If you were to look at it using a CCD camera and you wanted to actually get usable data on Lambda Andromeda, you would not get usable data on anything else because it is so bright. It basically will, it limits the exposure time that you can place. So basically how much light can you collect? And that means that anything that is faint, you will not collect enough light in order to get good data. or really even at all. And or it may not, the stars may not even show up in the background at all. So Lambda Andromeda star chart isn't all that useful. It is called HL Auriga. So I'm going to come back to this, and I'm going to type in HL Auriga. You know immediately that from the HL, that means that it is a variable star. The Auriga, or AUR, means that the star is in the constellation of Auriga. So immediately you know this is a variable star that is in the constellation of Auriga. Auriga is best viewed in the winter. So right off the bat, if I'm interested in a variable star in the winter, I know immediately this is an object I can look into. It is eclipsing binary. Specifically, it is a W Uma or W Ursa Majoris type eclipsing binary. So again, this is an example of this not being specific. Yes, it is an eclipsing binary, but there are a number of different types of eclipsing binaries. But again, you have the ICRS, you have FK4, so forth and so on. But let's go over here back to ALADIN. And so here is a star. This is zoomed in such that the field of view is about 4 arc minutes. Your field of view is going to be typically larger than that. Let's go to the field of view of the camera here at George Mason. Now, every telescope and camera system will have its own unique field of view. Generally speaking, no two fields of view will be identical. It depends on the focal length of your telescope and the pixel sizes of your camera. So for our camera here at George Mason on the 24-inch telescope, our field of view is roughly 25 by 25 arc minutes square. So if I were to take an image of it, of the sky, I would see some not facsimile, but something that looks like this. And in a moment, I'll show you an image I took at using actually a different telescope. But you can see that if you were just handed this image and asked which of these is HL Auriga, you might say, all right, yeah, the one in the center. But outside of that, it really doesn't have a huge distinction. There are other stars of comparable brightness. There is a star that is significantly brighter. There are many stars that are significantly dimmer. But other than the fact that it's completely centered in this field of view, nothing really distinguishes it. When in practice, when using a telescope, your pointing is never going to be perfect. And so your star, your target star, is never going to be, or very, very rarely, is going to be in the center of the field of view, in the center of the image that you take. It's going to be somewhere else in the image. Occasionally, a bright star may actually be in the center. So that is very worth noting, that do not take it for granted that the star that is in the center of your field of view is the star that you wanted the telescope to point to. All right. So again, we have SIMBAD. I click on SIMBAD. I think I click on SIMBAD. Nope. I click on SIMBAD, and you get these boxes. And you can see that HL Auriga is here. We have this star with a lovely name of HD 43456. Over here, this is a Tycho catalog star, and same with this one. Now, what is relevant to this is later on, we're going to be talking about differential photometry. Differential photometry is a method where we determine the brightness of an object relative to the brightness of another object in that field of view. I will tell you why that is important as we get into differential photometry specifically. So the reason why I'm really bringing this out and mentioning it is that if I want to know what the brightness of HL Auriga is over time, because it is a variable star, its brightness changes over time. So if I want to measure that, I need something to measure it against. And so I have to look at stars within the same field of view that are generally speaking, of comparable brightness. So I would use one as a comparison star, and then I use 2 or 3 others or more as check stars to make sure that my comparison is itself not variable. And so I can get good data on that. Now, let's see what you would actually see at the telescope. In order to do that, the easiest, there are a number of tools that you can use to display what is known as a FITS image. FITS is flexible image transport system, if I remember correctly. It is the standard via which astronomical images are taken. This is the standard format through which astronomical images are taken. This was developed because of, various types of images have various types of compression. And so comparing the fluxes you extract from, say, a JPEG to a PNG, you're not comparing apples to apples. So astronomers back in the 70s decided, you know what, we need to standardize this. And they created the FITS system. And so that is a way of doing that. Unfortunately for the general public, there are not a lot of applications that are readily available or pre-installed on your machine that will display them. GIMP will do so, Photoshop can do so. But I'm going to show you a tool that you can use as web-based that you can use in order to display a FITS image. And that is JS9 astronomical image display. You can type in the URL is js9.si.edu. But again, if you type into Google JS9 FITS viewer, then the first hit should get you here. And so you can see already this is a picture of CAS A, which is a supernova remnant. Now let me show you what an image I took looks like. That's the standard image on there. So I go to Open Local. So I come down here, I open that up, and boom, there is HL Auriga in all of its glory. Again, it doesn't exactly look like the image that I showed you with SIMBAD. It's going to be difficult for me to flip between the two, but I'll see what I can do. You can see here that we have those 4 stars that I talked about before. One of the immediate differences between this star field and the star field that you'll see in ALADIN on SIMBAD is what we call the depth of field. How faint can you see? Here you can see that we're only seeing a much smaller, the brighter stars within that field. Now, there is some, what's the word I'm looking for? What you're looking at right now isn't exactly all the information there. So if you go to scale, you get this limit, and you have these values, low and high. So this particular camera has what we call a well depth of 65,556. When I talk about CCDs later, I will get into more specifically what that means. But effectively, that means counts. That means how many, you can think of it as how many photons have been collected by each pixel at that location. And there is a limit. Prior to, or when you get more than 65,000, so forth, the pixel's full. Your rain bucket is full. You can't collect any more photons. But the display can only display things over 255 channels. So generally, what you will see is a histogram, or when you look at this, is a histogram. It takes certain values from a range, so maybe, all of the pixels from 1565 to 2065, it puts them all in the same channel. It makes all of those a certain shade of gray. And then the next block of 1,000 is a slightly brighter shade of gray. And so you have 255 shades of gray. And sorry for bringing that movie book into your head. Here we're displaying the entire, this image is displaying the entire basically brightness field. So what low and high means are that any value, any pixel that has a value of 1565 or lower, so from 0 to 1565, all of those pixels will register as black. Any pixel that has 51,587 counts or higher will be white. And then everything else falls into shades of gray lower down. So the easiest way I've found to deal with this is by changing the number. You can actually basically do something like that, where you just highlight. And you can see now I have changed the upper and lower bounds so that now anything that has counts lower than this 2200 value are black. Anything that has counts greater than 3700 are white. I'm going to change this to, and you can do this yourself to play around with this. Because you might start to see that depending on the scaling, you can bring out some of those really faint stars in the background. It is very important to note that when you are doing this, you are not changing the data. You are changing how the data is displayed. So the number of counts in this star is the same regardless of what I do over here in scaling it. So when I measure the brightness of the star, it's always going to be the same regardless of how it looks on my computer screen due to the scaling. So that is very important. I'm not manipulating the data. I'm manipulating how that data is displayed. So now we're back to SIMBAD. We're back to ALADIN. Here is the HL Riga. As I inadvertently did, if you click on it and hold, you can actually move the star field around. Oh, look, there's a galaxy. They're everywhere. So let's put it roughly back in the center. You can see that this star field doesn't really look the same as the image that I took. For one, the reason that there are more stars in this image than you can see in the image that I took. The other thing is the field of view is smaller. So right here, this is 25 arc minutes. But if I were to move it to, say, there, that is much more representative of what we're seeing in the actual image, the actual FITS image. The other thing you may have noticed is that the stars are not exactly in the same position, meaning that the optical system itself can do one of two things. Now, I will say that any operator worth their salt is going to have the camera orthogonal to or aligned with the right ascension declination axes, so that up and down are straight up and down are parallel lines of right ascension, and left and right is effectively parallel lines of, up and down is parallel lines of declination, left and right is parallel lines of right ascension. But because of the way the light reflects or refracts off of the optical elements within the system, your image can be flipped, meaning that left is right and right is left. Can be flipped such that up is down and down is up, or it can be mirrored such that left is left and right is right, or both. And so what you see on the sky may not be what you are actually seeing in this map, because they are taken using two different optical systems. So you get to do something like star matching, which I have to admit I'm pretty good at. I think my students can attest to this, but I've been doing it for a while. So this is not exactly easy, but I'll try to give you a couple of little tips to get you in the right place. First off, find something that is big, some kind of recognizable pattern of the stars that is sizable. And then you want to scale your map such that the size of that object, I'm using these 4 relatively bright stars, this square or this rectangle, and I'm going to zoom in so that the size of that system, or that configuration is roughly the same size as is roughly the same size as that in my image. So here again, we see these are my 4 stars. They take up a good fraction of the field of view. And so when I go back to the other screen, I now know which stars to look at when I'm talking about and doing star matching to figure out which stars are which based on where they appear or where they're located relative to other stars. This field is kind of easy to work with because it's got one star that is significantly brighter than the other ones. So that would be the first thing that you would go to, that I would recommend you go to, is check out this star. Then try to find a small grouping of stars that is unique or recognizable and somewhat unique. So if you look into this, again, it may not pick up too much on the screen, but if you look at this, you have the bright star, and then up and to the left, you have this little faint star, and then up and to the right, you have this medium-ish, or in comparison to these 2 stars, brightest star. So it's kind of like a dog leg in a golf course, or to me, it's reminiscent of the constellation of Aries. I also note that I have these 3 stars that kind of point to an arrow, and they point to the lower left in this orientation. Keep in mind these objects as I flip to the image in ALADIN. Okay, so here is the image in ALADIN. I go to this star here. It is the brightest star. And I look in its local environment or a local area, or it's very to basically close in on that star. And immediately you notice that there are more than 2 stars next to it. But I can find that over here, this is a reasonably bright star. It's definitely brighter than these little tiny ones. And then I dogleg over to this bright one, and that gives me my orientation. Or that is what I'm matching. And what I'm seeing here is that this orientation is flipped, such that these were pointed in opposite directions. This was actually above the star in my image, and now it's below. This star, though, was to the right in my image, and it's also to the right in SIMBAD. I come over here, I see these stars. These stars are relatively bright. They kind of form an arrow. So I now know if the image is flipped, mirrored, or both. And right now it appears to be flipped but not mirrored. And so I know that Lambda Andromeda, HL Riga, is this star. So in this image, it's up and to the left. In the image I took, because it is flipped, it is going to be left and down. And let's see if that's the case. And lo and behold, left and down, we have this here. And you can look at other stars and to verify that. But I know what I'm doing. I've looked at this many, many times. Trust me, that is HL Auriga. This is HD 44, yada yada. And these 2 stars are the Tycho stars. So now I know which star of these is my target of interest. Let's look at a different star. Before I go to another star, this is what we refer to as a loose field, meaning that these stars are relatively isolated. While there are stars that are kind of close, like this star is fairly close to this one, you can take data from that star without contamination from the light of that star. So you can find the brightnesses of these stars fairly easily without having to worry about contamination from other sources. Let's look at what we refer to as a crowded field. This is an image of what is known as a crowded field. Specifically, this is M13, the Great Cluster of Hercules, a massive globular cluster in the constellation of Hercules. This image was not taken at the Emery telescope like HL Auriga was. HL Auriga, its field of view from the telescope or from the Emery telescope is about 15 by 15 arc minutes. This telescope is a 20-inch telescope and has a different camera, and so therefore its field of view is larger. It's roughly what we have here at George Mason of about 25 arc minutes by 25 arc minutes. And you can do the same sorts of thing where you do scaling, and you can play around with it so that you can bring out the background stars, that you can see them on the display. Something to note, this is a raw image, meaning that it still has some artifacts in it due to how the image is taken and so forth. So that's what explains this little divot down here. But this is an example of a crowded field. And what I mean by that is, if you look at the center, if we zoom in on it, you can see that there are stars on stars on stars. So it is basically impossible to get reliable magnification, reliable photometry of stars in the core of the cluster. Because as I will describe later when I describe aperture photometry, you can't isolate each of these stars such that there is no contamination with the stars around it. The stars around it are contributing to the brightness of the object, of the target star that you are looking at. So if I look at, say, that star, there are a number of stars around it that are going to contribute to the amount of flux or brightness that I measure at that point. Even if you look at stars out here, some of these are also fairly crowded. So doing photometry on this is a bit more involved. And again, at a later lecture, I will talk about the methods to help cope with a crowded field. Getting photometry in a crowded field is not impossible. There's just a little bit more to it than simple aperture photometry. Now let's go back to what SIMBAD or ALADIN how it would display this image. So I type in M13. M is the Messier catalog. So this is the 13th object in a catalog created by Charles Messier. And this is what this star looks like on the digital sky survey. Field of view is roughly half a degree, so it's comparable to the what we were seeing in that other image. But the notable exception is you can't change the scaling on the images in ALADIN. So this is completely blown out, meaning that the entire core is saturated. You can't even tell there are individual stars there, simply based on the dynamic range of the camera. This is not to say that there is just one big chunk of light there. What it's saying is, in order to, or what this is in order to bring out all of these really, really faint star, the scaling has such that everything in here is basically white. All of these stars are considered to be white. And so it looks like a block image. And so it's trickier when dealing with this type of field, particularly if you're interested in stars that are over here, that are on the outskirts of the globular cluster. It's more difficult to find your stars because of that. Because there are so many different stars that it's difficult to find it. And if you're interested in stars that are really close in, for whatever reason, this would actually not be a useful tool because of the fact that it's so overblown. But I will leave it to you as an exercise. You can go back and look at the image again that I displayed in JS9 and this image, and you can figure out how this is oriented. For this one, what I would do is, again, I would look for small little areas of a pattern that is recognizable. I've got this one. I've got this really thin isosceles triangle, and then I would go and try to find them in the other image, with the understanding that these orientations may be flipped or may be mirrored or both. So I will leave it to you as an exercise to tell me whether or not the image that I'm showing of M13, which now that I'm looking at this is actually taken here. It was not taken at LSU. For those of you in my class, I will be giving you an image that was actually taken at LSU, but regardless, I will leave it to you as an exercise to figure out if it's flipped, mirrored, or both. All right, let us move on to VIZIER. So if I were to go back to the SIMBAD basic query, I can see up here something called VIZIER. Again, it's French. VIZIER is a catalog of catalogs, meaning that if I want very specific information about a star that is not in SIMBAD. So, for example, what is the period of the brightness period, the variability period of HL Auriga, and how much it varies? What is the from what magnitude to what magnitude does it vary, or what is the range of brightness difference that I can expect if I were to look at lambda and or HL Auriga? So what I would do here is I'm not going to I'm not going to put in HLR because it's not going to give me anything. Well, it says it's going to give me 1, but I don't trust it. What I'm going to do is I know that it is in something called the General Catalog of Variable Stars. And so what I'm going to do is I'm just going to put in General Catalog. What I'm going to do is I'm going to type in general, and I can see down here that there are 111 catalogs with that word in its title. And I'll just find catalog. And I'll go through, and I notice General Catalog of Variable Stars, SAMOS 2007 to 2017. Come over here, and I click on this blue thing, or this blue link. And that gets me to this. These are the various tables within this catalog. Basically, this catalog, this table has to do with its positional information. This has to do with magnitude information. This table has the periods that I'm looking for and all that sort of thing. You may notice these check marks on the side. Once I query this table, once I look for values, anything that is checked is actually going to pop up. So here, for example, I'm going to have GCVS, which is the General Catalog of Variable Stars, its identifier down here, and its variable star description located here. Then RA and DEC, variable type, so forth and so on, so forth and so on. So if I were interested in, for example, something like, what would be a good example? For whatever reason, I wanted to know what the RA and DEC of the star was in 1950. I would click on these two over here. Generally speaking, by default, is going to be information that is relevant to any kind of study of this star. And actually, it, in my opinion, gives you more information than you may want. So in other ways, you might want to click off some of these, such as exists. I don't really need that. I don't really need these. I don't really need these. So when I query this, I don't get a whole lot of columns. So if you don't type anything in those fields and you just hit submit, you're going to get the entire catalog if you just depending on your preferences. So right now I'm displaying this as an HTML table with a maximum of 50 entries. So yeah, so 50 entries. That way it's nice. But I can do 1,000 entries. Or if I have a really good internet connection, I can do unlimited, which means I can show all 60,899 stars within this catalog, all 60,000, 61,000 stars in this catalog. I'm not going to do that because it, takes a while to load. But you can see here that here are the stars that are located. I don't think it's query, but anyway, I have the right ascension declination. I have the designation T and, U and, V and, so forth and so on. I have the variable type. M stands for Myra. EA stands for an algol type eclipsing binary, so forth and so on. There are novae, cataclysmic variables, Cepheid variables, all kinds of variable stars. And so this variable type will let you know. If you click on that, generally speaking, and you can, if you keep clicking on links, you can get to a file which tells you what these variable types are. So R down here is a close binary system. EP are stars that show eclipses by their planets, so forth and so on. So you know what letters to use if you're interested in looking at only those stars within the catalog. Let me give you an example. So if I come back to this screen, and let's say I wanted a list of eclipsing, say I wanted a list of all of the algol type eclipsing binary systems in the catalog. I wanted to look at a sampling of algol type eclipsing binaries for a study on, say, the evolution of the period in these types of binaries over time. This catalog, as I just showed you, has a whole lot of different variables. So if I just wanted a list of just the algol types, I would type in EA, and then I would hit submit. And now it's going to display all of the stars within the catalog that are only designated as algol types. Again, depending on how you limit your display, you may not be getting all of them. So keep that in mind if you were to do this. And again, now we have all of these, you have the designation, you have the maximum magnitude of it, you have the period in days, spectral typing, so forth and so on. I thought I'd gotten rid of that, but apparently not. The last thing I will say about this is, let's say you want to only look at stars that are algol type and have periods of less than 2 weeks, 14 days. So let's go back to here. Let's go to the period, and you can use the mathematical sign less than 14. And now you can see that I'm only looking at stars that are algol eclipsing binaries with periods of less than 10 or 2 weeks, 14 days. And you can reorder this. You can reorder it so that now I am looking at this list as a function of right ascension and declination. So now I know, all right, if it's the summer, these are the stars that I would want to include in my sample for observing at that time. Winter, then I would want to look at, stars that are in the like 6 hours, 6 hour range. And so this is a very useful tool in terms of creating target lists. If you have you want to look at the characteristics of Cepheid stars, and you will only have a certain window of time in a year that you can do this experiment or do these observations, and you have a certain time frame in which you can only do them at night, then basically you can create a list of targets based on any number, based on a number of different characteristics within this particular catalog. Now, if you are looking for, I have, for example, a catalog in here, not to toot my own horn, and you see it here, near infrared photometry variability in row Ophiuchus. Click on that, and I have two tables. One, the entire catalog of stars I looked at, the entire sample or entire target list, and then I have the stars I identified as variable. And so, again, same sorts of thing, where you can, here, if you're interested in young stellar objects in the row Ophiuchus star forming region, then you can query it by magnitude, you can query it by variability type, that sort of thing. So, okay, well, that's all I've got for you today. Again, these are tools that are very often used by astronomers to get information about targets, or at least the starting points of information about targets, and tools used to identify the targets from images that were taken with a particular telescope, and also catalogs that allow astronomers to develop target lists for basically projects that deal with a class of object and not a specific star here or there. So, all right. I hope you enjoyed this lecture, and next lecture will be on basically light in the sense of the magnitude system and filter sets and things of that nature. So when I was talking about photometry and how to measure the brightnesses of things, that's what I'm going to be talking about in specific next time. So peace out and clear skies.